I'm giving kind of an overview talk for the work that's being done as part of the SAGES collaboration, using globular clusters and halo stars to try and unravel the star formation and assembly history of galaxies. So the SAGES collaborators on this work are shown here. The yellow people are the ones that are either in Santa Cruz or about to be in Santa Cruz quite soon. So for those of you that are not globular cluster aficionados, just a few words about why globular clusters are useful in trying to understand galaxy formation. Well, first of all galaxies, pretty much all galaxies above a very low mass threshold have a retinue of globular clusters. So they belong to galaxies of all morphological types. And the idea is that globular cluster formation accompanies all the major star formation episodes in a galaxy's history. But the really good part is that once formed, globular clusters are unchanging beacons. They're basically along for the ride in all of these mergers and acquisitions that take place to assemble the galaxies we see today. And using the properties of globular clusters, we can back out some of those details of the assembly history. And I just want to remind you that in the watershed paper back in 1978, Searle and Zinn used globular cluster velocities, metallicities, and positions to understand that the Milky Way galaxy had a two-phase assembly history, or an inside-out assembly history. So that's a sort of a precursor to the work that we're doing in the SAGES group today. So one thing you need to know is that there are distinct metallicity subpopulations in galaxies. There are, when you plot in an individual galaxy the number of globular clusters as a function of color, you typically see two peaks, a blue metal poor peak and a red metal rich peak. In principle, these two peaks could come about from an age difference, but in fact we know, because my group spent a decade or more getting spectra of globular clusters in external galaxies, we know that the vast majority of these things are old, and so this is indeed a metallicity separation. Now, up until very recently, we supposed that the metal poor ones were a year or two older than the metal rich ones, but our ability to measure age from low resolution spectra was not able to resolve those kinds of age differences. Theoretical attempts to explain this metallicity bimodality, or the presence of distinct subpopulations, would seem to be requiring an ad hoc truncation mechanism whereby you truncate metal poor globular cluster formation at high redshift. One of the possible mechanisms was cosmic reionization. Nonetheless, no matter how this bimodality comes about, it's pretty ubiquitous. And if you look at globular cluster scaling relations, they clearly indicate that globular clusters are setting constraints on hierarchical merging. For instance, here's globular cluster metallicity against host galaxy mass using absolute magnitude as a proxy. These are the red peaks of the bimodal distributions in a whole bunch of galaxies, and these are the blue peaks. So the point is that we can use globular clusters to set constraints on host galaxy assembly. So this is the mass of the host. And the red globular clusters, even very early on, seem to slave very closely to the galaxy bulge population, and the metal poor globular clusters seem to be tracing the halos. This has been borne out by more recent work. This is a nice plot from Jay Strader's work, where he's looking at the distribution of the metal-rich globular clusters in red, and that metal-rich subpopulation very closely corresponds to the distribution of bulge starlight, whereas the blue globular clusters are much more extended. Again, a real distinction between these populations, and this is quite a general result. More recently still, from our survey work, work led by Vince Potter, the metallicity subpopulations are also kinematically distinct, and giving some additional ways to understand galaxy assembly. So very recently, at the end of 2011, Chiara Tonini showed that the bimodal distributions that we see come about naturally as a result of hierarchical merging, hierarchical galaxy assembly. And this is just a consequence of the mass-metallicity relation, if you like, where larger things are more metal-rich. So when you have a paradigm of accretion onto a host galaxy, the accreted galaxies and their globular clusters are going to be of lower metallicity, and so they systematically populate the blue peak of the bimodal distribution. So she's taking merger rates and merger rates as a function of mass from dark matter simulations. So the point is that her model produces red globular clusters about a redshift of 2, and the metal poor globular clusters formed earlier at redshifts between 3 and 4. And her models actually reproduce these scaling relations very well. The other important new result is that nowadays we can do much better with the age dating. So we're using white dwarf cooling sequences, we can get ages to about half a gigayear. So on this plot, this is a metal-rich globular cluster, this is a metal-poor globular cluster, and indeed, the red globular cluster seems to have formed at about a redshift of 2, and the blue globular clusters are about 1 or 2 gigayears younger. So this is all starting to sound consistent, and consistent with our general, previously hand-wavy understanding about red globular clusters tracing bulges and blue globular clusters tracing the buildup of galaxy halos via accretion. So this links directly into our understanding of two-phase galaxy formation. Everybody here is probably familiar with this idea. You form a nugget at redshift of 2, say, and you grow it by continual accreting of lower mass satellites up to the present day. And of course, the more mass, this is half-light radius against mass, the more massive the galaxy, the more accreted material and the larger its size. So we, in our group, decided that the most interesting thing we could do in trying to constrain these ideas was to look at large galactocentric radii. So previously, there had been very influential surveys, like the Sauron survey, looking at, and subsequently the Atlas 3D survey, that looked at the central regions of galaxies and made two-dimensional maps of those areas. But notice that 90% of the mass and the angular momentum in galaxies resides outside one effective radii. So if you want to understand the assembly of galaxies and their halos, you are likely going to need to go much further out. That motivated the Slug Survey, which you've heard a bit about from Kristen this morning, where we've got actually 26 galaxies where we look at their globular cluster systems out to 10 effective radii and their field starlight out to 3 effective radii. So a range of properties and characteristics and environments. So next slide here, we get two-dimensional maps, wide field two-dimensional maps of the starlight by using a technique that allows us to basically employ DMOS, the DMOS multi-object spectrograph, as a pseudo-IFU. So our results are velocity maps like this. This is the Sauron field right in the center there, and we're able to produce two-dimensional maps out to several effective radius. So the initial results from this Slug Survey, the first few galaxies we analyzed, really reinforced the need to go to wide field. So these galaxies, is V over sigma against radius. These galaxies would all have been classified as fast rotators in the Sauron survey. And you can see as you go out beyond that radius, they're all over the place. So the inner profiles do not predict large radius behavior. So in other words, if you want to understand galaxies, you need to look farther out. So one of the things that was intriguing to us as globular cluster aficionados was the simulations that Avishai Deckel and Daniel Severino and collaborators were coming up with, these cosmological simulations, which we like to talk about as wild disks, but Avishai calls them VDIs, the violently disturbed something or others. Violent disk instabilities, that's it. So anyway, I like to call them my wild disk because I can remember that. And so this, just to refresh your memory, is disks that form at the intersections of filaments of the cosmic web, where material flows in, making these small disks. The disks are clumpy and turbulent, and the disk instabilities cause these clumps to migrate to the center, where they form something that looks an awful lot like a classical bulge. So we noticed that these clumps have about the right size, they're formed at about the right redshift with the right metallicity to be the hosts of globular clusters, metal-rich globular clusters. So of course you're allowed to evolve those wild disks passively to the present, and maybe they become the lenticular galaxies of today, or you're allowed to merge them and perhaps form other galaxies, early type galaxies. Well, with our survey, we're in a good position to actually test these different ideas about how you form the nugget and how it assembles its halo. So what we've been able to do is produce two-dimensional velocity maps. Here's a subset of some of our maps. These are actually selected to show the wide field velocity behavior. They're actually maps made from globular clusters, starlight, planetary nebulae. We include planetary nebulae information where we have them. And we've selected edge-on cases, so flattened, presumptively edge-on galaxies, because this avoids the issues with projection effects, inclination angle, and so on. So when we do these observations, so these are real data now, what you can see is there's generally rapid rotation, aligned rotation at the centers, and this falls off with radius. Now this fall off, this general result that the velocity field is falling off with radius, is a surprise, because it isn't predicted from a major merger scenario, where major mergers are expected to fling angular momentum outwards and cause a spin-up. So as we're seeing this over and over again, we're starting to feel like we have some interesting constraints. Notice that sound would have completely missed this declining velocity profile because the field of view doesn't encompass the region where this decline happens. So once we've got our data maps, our two-dimensional maps, we need to compare those to simulations. So what we've been doing is we've been taking the simulations and converting them to a form that we can observe. So we're observing the simulations, making maps that are directly comparable to the maps from the observations. So here's a series of 16 different merger simulations, 1 to 3 merger simulations, and the general trend here is that we see strong aligned rotation going out to large radii. In many cases, the rotation actually increases with radius. Now you can produce a declining wide field rotation with a major merger, but you basically need a low angular momentum one-to-one merger, and we know those are rare, so we can't invoke that to explain all of the observations we see. And in the simulations we often see pretty strong kinematic twists, and those are not generally seen in our data maps, our observational maps. But the cosmological simulations do a much better job of reproducing what we're seeing in the data. So you have the aligned rotation, in many cases strong in the center, declining as you go outwards. So for each of these simulations, these are individual different simulations with different input parameters and so on. We have time sequences for each of those. So this is the same thing, only in plot form, perhaps a little easier to digest. V over sigma against R, where you can see this declining rotation at large radius, but well beyond where you would see it with the standard integral field unit survey data. And over here is a sort of summary plot of the simulations. Merger simulations pretty much always do this. You can mess about with the mass ratios and so on, but the result is basically the same. And here's the cosmological simulations looking very much like the data. So we're not seeing evidence that major mergers are a dominant mechanism for building the galaxies we see today. Just hasn't happened. So in my few remaining minutes, I thought I would just give you a slug survey update. I've only been able to skim the surface of some of the things that we're doing as part of the slug survey. So I'm just going to tell you incredibly briefly about some of the other highlights, and you can perhaps go to our website if you're interested in more details, or ask any of the yellow people that I mentioned at the beginning. So the slug survey, the observational part, is nearing completion, and as we're ramping down on the observations, we're ramping up on the interpretation, analysis and interpretation. But we already have about a bit over 30 papers now published. Some of the recent highlights, well, we have 2,500 globular cluster velocities to good quality, 15 kilometers second accuracy velocities. In 12 galaxies, more on the way. We're showing that the metallicity subpopulations are kinematically distinct and using them to unravel the details of individual galaxies' assembly histories. We have almost 1,000 spectroscopic metallicity measurements for the globular clusters, showing that metallicity bimodality is a general result, and looking at color metallicity transformations. We've got Jacob Arnold's about to submit a paper with 23 galaxies with two-dimensional velocity maps. I've already talked about the work that Aaron's leading on the velocity maps and their comparison with the cosmological and other simulations. We also have two-dimensional stellar metallicity maps for about 10 galaxies so far, more to come, from calcium triplet observations, and they're being compared with theoretical expectations as well. That's work led by Nicola Pastorello. We've looked at radial metallicity gradients in galaxies, evidence for two-phase assembly again. Aaron told you a bit about the substructure work, where we can estimate the mass of accreted objects and even the timing of the accretion event, looking at information that's only available in velocity, position, phase space. So for galaxies that look completely placid, red and dead, we can still see how they put themselves together. Of course, with a survey like this, you always have serendipity. We're actually discovering new classes of object. For instance, this is a picture of a new class of ultra-compact dwarf galaxy, hitherto unknown, a faint version of the classical UCD, and at first blush, not so different from bright or faint globular clusters. And Jay Strader's about to submit a paper on our work on M60, where we've discovered the densest known galaxy. So a lot of good stuff going on. You've heard from Aaron and Kristen about this morning, and I want to mention Duncan Forbes is going to be talking about more slugs work later in the week on Thursday. So I'm done now, but I'll just quickly review what I told you. The recent results that have been very important, metallicity bimodality is real and ubiquitous, so don't let anybody tell you otherwise. It occurs naturally in models of hierarchical galaxy assembly. These new white dwarf cooling ages confirm what we suspected all along, that the metal poor globular clusters are older and by about a couple of giga-years than the metal-rich ones. So the globular cluster scaling relations constrain galaxy assembly. The metal-rich globular clusters trace the buildup of bulges, and the metal-blue globular clusters trace the buildup of galaxy halos. And in fact, they're one of the very few ways you can look at galaxy halos for galaxies beyond the local group. So our SAGES Slug Survey is producing a large quantity of data for a bunch of nearby galaxies, globular clusters to 10 effective radii, starlight to 3 to 4 effective radii. And we're able to make some quite interesting constraints on two-phase galaxy assembly. We conclude that the halo buildup is indeed dominated by minor mergers, and major mergers are actually consistent with this general result of inner rapid and low outer rotation. So the cosmological simulations, these wild disk simulations, seem to do quite a good job in matching the data so far. But there's a lot more to see, so I welcome you to our website. Thank you.
All right, let's start with David.
Do you expect to see some signature of the contribution of clamps produced by violent dynamical instabilities to the bulge in terms of metallicity, abundance ratios, or time scale of function?
Yes, yes. So there was a paper by Shapiro et al. They actually did some observations of clumps in supposed wild disks. So and they found them to have a metallicity that was very similar to metal-rich globular clusters, and also, you know, the gas, the general metallicity, ambient metallicity, if you like, at the time of formation was suggested about a redshift of 2.
And that works with the alpha element of iron ratio as well? Or?
Well, we haven't got alpha to iron measurements in most of these observations. That's a bit harder to do because we only have, you know, these objects are, you know, 50 megaparsecs away, generally speaking. So that's a harder one to do, the alpha. Be nice.
Question? Yeah.
So, in the paper sigma versus the radius of the galaxy, you see that beyond one effective radius, then the galaxies are all over the place. Is that correlated with the environment?
Well, the all over the place kind of went away when we were able to eliminate the projection effects. So so that's why I showed you a map that was restricted to the flattened ones that presumptively edge on, and then they all sort of fall into line.
So they are decreasing.
They're all decreasing.
This is not dependent on the environment, so it doesn't, because I guess that you have some of them in Virgo, so
We do.
that's quite more dense than any other
Correct.
environment. So
Correct.
it's not correlated with that.
Right, but we are in early stages yet. So the ones that aren't edge on, then it will be interesting to look more at their environments and see if we can separate out the projection effects from other effects. So yes, that's something that will be coming.
Although I can add perhaps to that, tomorrow I'll show another 30 or so Virgo cluster galaxies that corroborate what Jean has shown. This is based on long slit data beyond 2 RE, so it's a great result. Anatoly first and Sandy.
But globular clusters and clumps in wild disk instabilities, I thought that wild disk instability clumps are way too massive and not globular clusters.
They're more massive than globular clusters. That's right, but you need a more massive initial molecular cloud.
That's not the point. The point is that if they're too massive, dynamical friction is way too big, and they suck it into the center. They are not part of the globular cluster population at present.
And that's what happens in the simulation.
The clumps go to the center. Yeah, but the globular clusters are in the center too of the galaxies. They're in the bulge. The red globular cluster in the bulge.
Not with that mass. It's 10 to the 8 and the 9 in the mass. It's sucked into the center. It's a seed there. It's not globular cluster.
If you have a bulge, I mean, the simulation to make a bulge, but it's got some scale, like when you includes, it goes.
It forms in a disk, sits in a disk, and sucked into the center. You cannot get it to the 20 kiloparsec distance.
But the voltage extends to 20 kiloparsec, well, more like 10 kiloparsec. These
Not
are
the
these
simulations. You cannot
Not in
get
the
that to 20
simulation.
kiloparsec.
yeah, and the ART simulations.
Well, let's discuss the cloud spectrum, and we'll have a discussion here at the end of the session. Sandy?
I was wondering what the current thinking is on survivability of globular clusters. And that relates to the related interesting question of counts. And so you emphasize the scaling laws for the peaks of those distributions. I was wondering what we see about the relative numbers of objects in the peaks as a function of other galaxy properties. And furthermore, the really big question is, in looking at today's globular clusters, are we looking at like a few percent remnant population? At one time, the thinking was that most globular clusters got destroyed by dynamical friction or disk shocking or things like that. So I'm actually asking a bigger question about the survivability, and do we understand that well enough to model that?
Well, the work that we're doing sort of enters the scene after the initial phase where a large number of globular clusters are destroyed. So we're looking at after the first few million years where you do have a very substantial elimination of the population. But the work we're doing assumes that once you've formed those globular clusters and you've got rid of the initial loss, they're basically there. They're there and they're along for the ride every time you do a merger and have an accretion event. So, but the relative numbers of blue and red globular clusters is an important diagnostic. If you look at Chiara Tornini's work, her present day sort of 10 to the power 11 galaxy, about 70% of the blue peak in the distribution comes from accreted objects. So if you change some of the cosmological parameters in these dark matter simulations, you change the merger rate and you actually change how many clusters you expect in the blue peak. So to put that backwards, you might actually be able to constrain those input parameters to the simulations by looking at how the red and the blue peaks change. And obviously we have that information for these galaxies. We haven't published it yet because it's a very non-trivial exercise to get those numbers right. The number of globular clusters that's not a trivial number to give. We can give, crude ones, but to really get that right, because you're going out to large radius in these galaxies, counting globular clusters is non-trivial, but it will be done as part of our survey.